Hi, this is my electric car, which is a 1988 Soleq EVcort. And this here is the motor controller, which failed shortly after I bought the car. These are kind of unique and particularly complicated controllers in that they control the field and the armature of the motor separately. So I've since bypassed the controller and replaced it with two Curtis 1221C controllers, which are 1990s era controllers, one for the armature, one for the field. There's one for the armature in back of the battery box here. The field controller is underneath this DC-DC converter, which is also a modern replacement. These do tend to fail. And as far as I know, no one's ever succeeded in repairing one other than Soleq, the company that originally built them. Of course, they went out of business years ago, but we're going to give it a try. So I think I've disconnected all the cables here. This cable goes to the ammeter and voltmeter in the cabin. This cable goes to a bank of LED lights indicating controller conditions. This yellow connector is the ignition. This is the connector to the original DC-DC converter, which again we've bypassed. And this is the connection to the potentiometers for the accelerator and the regenerative braking. And then over here, which I've just attached, is this big 350 amp Anderson power pole connector, which of course goes to the main battery. This goes to the heater, so the heater connection here will have to be rewired. And of course the motor we've already disconnected when we bypassed the controller with the Curtis controllers. So I think we're ready to take this out here. Looks like first I'm going to have to remove the bumper as well as the headlights. Okay, I think we got everything out of the way and ready to do the extraction here. Okay, I got the controller into the basement. I'm going to try to open it up here. And it's resting on the heatsink. And then we have a cover. Looks like it's held down with a bunch of nuts all around the bottom, and then on the side with the cables there are these nuts. So this is going to have to lift straight up, and these screws have an internal hex, which is 5/64. So I think once we get these nuts off, we can take out the screws with an Allen wrench, and then hopefully this whole cover will lift right off. Well, that's encouraging. It says right on the case here, do not attempt to service. And again, I think no one has ever repaired one of these except for Soleq, the company that built it. But let's open it up and see what's inside. See what these hex screws are like. They do seem to unscrew, although they're pretty tight. That's one. Looks like there are about 8 of them. This one just doesn't want to turn anymore. Come back to that later. Well, a couple of these, they come out to a certain point and then they won't turn anymore. So instead I'm going to try to just screw it all the way in so that this lip can clear. And so far it's still going in. And I think that's all the way in. Okay, I got all the nuts on the bottom loose here. And on the side, I got 4 of the studs out, and 4 of the studs I had to screw all the way in. It wouldn't come out. So now I just have to see if we can pry this top off. It actually seems to be coming up pretty easily. So the problem is that this panel with all the wires seems to want to move with the cover. And I think obviously that's not right. This has all got to stay in place when the cover comes off. I'm not sure how to do that. Might have to remove these little studs, try to slip this straight back rather than lifting it up. Okay, well, I've removed 2 studs on each side and removed all the studs on this side, the side with all the wiring, except for one stud which I screwed all the way down instead. But let's see if that's enough to get the cover off. Well, looks like it's coming. And there it is. Not even sure what all this stuff is. Looks like some big relays in there. Circuit boards and giant capacitors. And then down here we've got just banks and banks of little power transistors. There's some diodes. There's a busted resistor. I don't know what that's all about. More power transistors. And that's about it. So I'm just going to go through this, see if I can figure out how these things are connected. And we'll go from there. So I don't have a full schematic of the controller, but I have two sources of information. One is the 1979 patent application by its designer, Sunjiro Oba, the head engineer at Soleq. It explains the basic principles of operation and includes several partial schematics. The second source is an owner's manual for the 1992 version of the EVcort, which had a similar controller, although with many revisions. This manual also contains a number of hand-drawn partial schematics. The Soleq controller was very unusual in that it regulated the field and the armature of the car's brushed DC motor independently. Consequently, it was one of the earliest EVs to have regenerative braking. Instead of the usual MOSFETs, the EVcort's power circuits used dozens of more primitive bipolar transistors wired in parallel. Although high-power MOSFETs were widely used in EVs by 1988, they weren't available when the Soleq controller was designed, and Soleq chose to stick with bipolar transistors right up until the end of production in 1994. When my controller failed, the car gave a jerky bucking response before going completely dead, and I suspect that was caused by a chain reaction of shorting and burnout of all those parallel output transistors. So I'm expecting some pretty severe damage. Okay, so just comparing this to those two reference sources, I think I've traced down the main power circuit. Here we have the positive lead from the battery connector, and that's connected directly to this contactor. You can see the big copper contact there. So that's the main power switch for the whole unit, going to the positive terminal of the traction battery. And then this is a relay that presumably turns this contactor relay on, and you can actually see the connections inside here, and the ones from the coil show continuity to the ignition. So presumably this relay then activates this relay to turn the unit on. And then here we have most of the control boards. In fact, this one says control board. And conveniently they're on a hinge. So you can lift this up. And underneath that are the main power transistors for the armature. And there's 100 of them. There's 5 boards, 2 rows of 10 transistors on each board, apparently identical, and they're all wired in parallel with these bus bars. And the collectors of those transistors are wired directly to the motor output, the negative terminal of the armature for the motor. And then over here, this has got to be the low voltage power supply. It has a surprisingly large transformer, creating the 15 volt low voltage power supply for most of the circuitry here. And then there are 2 other boards that have bus bars and parallel transistors on them. And this one I've identified as the driver board just by comparison to the schematic in the 1992-1994 manual. And it's got NPN transistors up here, PNP transistors down here, And then you can actually trace this green wire. It goes down here, connects to some diodes, and then comes out over here and that's connected directly to the bus to all the bases of the power transistors. And of course over here, large capacitors. These are just right across the battery input. Bunch of other little capacitors. And then over here is the other board that has bus bars. So another board designed to transmit significant power. This turns out to be the chopper for the field. You can actually follow the wires out to the cable for the field connections. And here we have a shunt which measures the current coming from the battery and then feeds that into the various control circuits. So that's an overview. Don't know what most of these control circuits are. There's a bunch of integrated circuits and a few small power transistors. And again, not sure what all this stuff does. But I suspect the problem is in the main power boards. So let's just start testing them. Okay, I guess we'll start by trying to check some of these output transistors. But meanwhile, notice over here, these are the flyback diodes. These allow current to flow through the choke and the motor when the transistors suddenly turn off. And one of these connections is broken off. Here looks like some of these melted, maybe shorted out. And here's another one that's completely detached. So hard to imagine how that happened, but looks like a pretty catastrophic failure. But anyway, let's try to look at some of the power transistors here. So the armature output here has 100 of these little transistors wired in parallel. So there's a collector bus here which just connects all the collectors together, which is the case of the transistor. And then there's this copper emitter bus, and the emitters are connected to that through these 0.07 ohm resistors. And then, hard to see it there, but behind it there's a smaller copper base bus, and that connects to each base through a 1 ohm resistor. So these old TO3 transistors have a common pin out, and you can see there's an offset here, and if that's facing up, then the left is the base, the right is the emitter, and the case is a collector. So we can test these on the diode setting. And I know these are all NPN, so forward direction is going to be positive on the base, negative on the emitter, so base to emitter is 0.59 volt, which is reasonable. Base to collector Same thing, 0.59. And in the reverse direction, emitter to base, open circuit, and collector to base, open circuit. So let's go ahead and check some of these transistors on the diode setting. And not sure how well this is going to work because we've got 100 of them connected in parallel, but we'll give it a try here. So the collector, all the collectors are connected together on this bus, so we'll just put minus terminal on that and go forward direction. So here we're going diode setting. Base to collector, and that's a short circuit. Base to collector, short circuit, short circuit, and it's looking like all of these are a short circuit, base to collector. So it could be that all of these transistors have been shorted out. Just to be sure that's gone through the transistor, let's go from the base to the base bus here. And that should be going through a 1 ohm resistor. Let's put it on resistance. And that's reading an open circuit. Open circuit. Open circuit. So it looks like these base resistors, 1 ohm resistors, are all blown out. Let's just check a base to collector on the resistance setting. And that's still reading a short circuit. So let's try going base to emitter. So we'll clip on the emitter here. This again would be the forward direction. Let's go back to the diode setting. So base to emitter. And that's reading an open circuit. Let's try another one. Open circuit. Another one. That's an open circuit. Oh, that's a short circuit. Let's keep going. Open circuit. Open circuit. Open circuit. Open circuit. And that's a short circuit. So nothing looking like a normal transistor here. They're either short-circuited or an open circuit. Let's look at some of these emitter resistors. So we'll turn this to resistance. And this will be emitter to emitter bus, and it looks like that resistor is open. Let's try this resistor. Now these are only 0.07 ohm resistors, so it's going to read as if it's a short circuit, and that's reading a short circuit. So it seems like either the transistor is shorted and the resistor has been blown open, or the resistor is intact and the contact in the transistor has been blown open. So I'm just going to go through all of these and see what the story is, but looks like probably all 100 of these transistors are shorted or blown out. So just to summarize, here's the basic armature circuit with 100 transistors wired in parallel and small resistors on the bases and emitters. The testing showed that all 100 transistors are blown. The most common pattern, seen in more than half the transistors, is a short between the base and collector, with an open circuit between the base and emitter and an open base resistor. In most of the remaining transistors, the pattern was similar, but the base was shorted to both the collector and emitter, and the emitter resistor was open. Remarkably, there are a few cases where both the emitter and the emitter resistor were open circuits, and finally one case where both resistors were intact and the emitter and collector of the transistor were both open. So in retrospect, I think I have a pretty good idea what happened. When the controller failed, I was descending a pretty steep hill with the batteries almost fully charged, and I put on the brake. That would have engaged the regenerative braking by applying sufficient voltage to the field that the back EMF of the motor exceeds the battery voltage. But instead of a smooth deceleration, the braking was sudden and severe, something I'd never experienced with the car before. But the only explanation I can think of for that behavior is that the motor must have generated a voltage spike that overloaded and shorted out one of the flyback diodes, providing a direct short across the armature. You recall that at least two of those diodes showed physical signs of damage. When I got to level ground and pressed the accelerator, that would have sent the full pack voltage through the shorted diode and onto the power transistors, resulting in a massive current pulse. And if any one of the 100 transistors developed a collector to base short as a result, that would send high voltage through the base bus and possibly set off a chain reaction of failures until all the transistors were blown. And that's what I think happened. Believe it or not, this is actually good news because at least we have a pretty good idea of how these circuits work, so we might be able to repair or replace them. If the problem were in the much more complicated control circuits, that would be much more difficult to diagnose and repair. So here's a schematic for the driver board, and this is a later version, 1991. It has just 2 transistors in parallel. Ours has 5. But otherwise it's pretty similar. Here's these copper bus bars. Here's the PNP transistors that provide the positive side of the pulse. Here's the NPN transistors that provide the negative part of the pulse. And here is the green wire, thick green wire, that goes from the driver board to the banks of output transistors. Here's those diodes that we saw. Now, since the output transistor shorted out, it's possible that high voltage could have come back through this line and maybe shorted out something in the driver board as well. So let's try to check some of these transistors in the drive board. Okay, so in order to check these transistors in the driver board, what I've done is removed these 3 screws, and those screws connect the case, which is the collector connection, to the bus bar, and I can see that there's no other connections to the case. And then for this middle transistor right here, on this transistor I've disconnected the resistor that goes from the bus bar to the emitter connection. So that transistor also has a free emitter, and we're just going to check these transistors with the diode setting on the multimeter. So let's first try the forward direction, and this is the base. All of the bases are connected together in parallel. And I think these are NPN, so this should be forward direction, 0.47. There's another one, 0.55, and 0.46. So let's try reverse direction. Here's the base to collector, open circuit, open circuit, open circuit. So it's possible these drive transistors are still okay. Now let's try this one emitter that's free. That's the one with the broken resistor. So reverse direction looks like open circuit. And let's try the forward direction. 0.55. Same as the base to collector. So it looks like at least this transistor is good. Now the other ones, the emitter connection is really more difficult to disconnect. So I'm not going to do that. I'm going to assume these are probably okay. So it could be that this thing is working right up to the driver circuits, and it's only the final power stage that's broken. So on that optimistic note, I think we'll end part one. Next, I'll have to figure out some way to power this thing up outside the vehicle and verify whether the upstream control and driver circuits are still functional. And if that checks out, then come up with a plan to replace all those blown output transistors. So it's going to be a lot of work, but it does seem there might be a real possibility of reviving this controller. So stay tuned, and thanks for watching.